Thanks to everybody for coming. It's a pleasure to welcome you here to this meeting on antimicrobial resistance in Boston, which sometimes is nice and sunny, and you can sail like that. Today is not, but we're going to work on that. A special thanks to people who have traveled to come here. It's occurred to me as I've been at recent meetings that traveling has a lot of real costs in terms of lost work, which you maybe make up on the plane, but also lost time with family and friends. And the conference really has to be pretty interesting to make it worthwhile. So I hope you will find that this one is, and I'm grateful to everyone we are grateful to everyone who's come. Some thanks to the organizing committee and chairs of the sessions who are listed here. Special thanks to Kevin Outerson from BU Law School, who is organizing the last session on policy, which is a really unusual feature of this meeting, which I hope the scientists will find as interesting as the policy people, and also for providing a great venue here at BU. Special thanks to the people who have made this meeting happen. I've been fairly out of it on the logistics, which is just how I like it, and that only works with great people doing it. So you've met, some of you, Alyssa, Felissa, and Mel from our group, and Elizabeth Agate from here at BU, and they're in the back, some of them, and so you will probably be talking to them later if you have questions about the meeting. And then also thanks to BU Law School for providing the facilities, and to Midas and the NIH for funding the conference. I'm going to move this. Can't block the NIH, that's bad politics. Okay, next comes excuses, which have to do with time and space. The one about time is that as we were finalizing this program, I was sitting in about the 9th hour of a long meeting in Geneva and thinking, I really want to get to that delicious Swiss wine, and I'm tired of sitting here in this conference room. And that reminded me that it's better to have a little more focus over a slightly shorter day. So we have cut 5 minutes from every speaker from what they were originally allotted, and then put the discussion at the end of each session. I hope you will find that trade-off worthwhile, and I hope you'll admire my leadership qualities in being willing to slash 20% without consulting anyone. I think there's anyway. On the same topic of time, we are going to keep the introductions to pretty much people's names, because you have good bios of people in the packets, and we want to maximize the time for the speakers. The reason the airplane is on here is to remind me that as we were organizing this meeting, there was some tension in our minds between the fact that we could actually have a really great meeting on antimicrobial resistance with only people from the Boston or New England area. There's a lot of great work happening throughout this area, and the tension was between trying to hear about all of that, and on the other hand, bring in some of the people from further afield whose work we as the organizers admire, but who we don't always get to meet. And so one of the things I'm excited about is that the number of the speakers are people that I haven't met and that the other speakers haven't met. So that's kind of the rationale, but apologies for the somewhat underrepresentation of the exciting work that's going on in this part of the world. So to move on to the scientific topics, I just want to say a couple of things about kind of why we care about antimicrobial resistance and how I think some of the more specific topics fit into that. And then I want to raise what I think are a couple of the really interesting and hard questions that sound academic and are academic about antimicrobial resistance and the population thereof, but also I think have a lot of relevance to trying to solve some of these practical problems. So why I think we care is that we want to make antimicrobials, we want antimicrobials to help us reduce the burden of disease, incidence, duration, and severity, and we want that to continue for a long time and not to be fleeting fact of the late 20th and early 21st century. And a lot of the scientific and clinical work and even policy work on antimicrobial resistance is trying to achieve means to this end. One of those is improving treatment. That goes at least as far back as Paul Ehrlich in 1913, who wrote in The Lancet pretty much the modern principles of chemotherapy for infections like HIV and TB, although he was writing about another infection. But he wrote about hitting hard and hitting early and combining therapy to prevent the emergence of resistance to one of those. And it's a sign of the times that a German writing in a English journal felt compelled to write it in French. Frappe fort, frappe vite. A second means to that end is to the end of improving treatment and preserving antimicrobials is to prevent selection on innocent bystanders. These are some of the normal flora, color-coded by their Gram staining. And they live all over and within us, and a lot of what we spend time trying to figure out is how to improve treatment so that those guys don't see as much antimicrobial selection. Another means to the end is to try to reduce transmission of resistant strains, so not only prevent them from emerging within an individual, but then try to prevent them spreading in the population. And mathematical models, about which you'll hear a lot in the next 2 days, are one means toward that end. On the more policy side, the need is to improve incentives for prescribing, to improve people's and hospitals and health plans' choice of formulary, and to conserve. Information is one means toward that end. Giving away free antibiotics is maybe, as several pharmacy chains do, is maybe not one of the best means toward that end. But this is the landscape on which these issues occur. Information is a big means to this end, and a lot of people spend time trying to develop better diagnostics and better awareness of what's going on. And you'll hear more about the surveillance and less about the diagnostics because of the more population focus of this meeting. But I think one of the really interesting questions is how we use surveillance to inform prescribing, and I'll talk about that in a minute a little bit more. And then how to use diagnostics to reduce the mistreatment of infections and improve the ability to prevent the emergence of resistance during treatment. Something funny has happened. Right, so then the last means to this end is research and development, and research can be basic research in terms of understanding how antibiotics kill, how bugs become tolerant or resistant, and the genetics of transfer of these resistance mutations, and not only mutations, but plasmids and other more exotic cassettes. And then, again, in the policy session, you'll hear about the interaction between piles of money and piles of drugs, and the need to try to stimulate new drugs and new classes of drugs by economic, legal, and other incentives. So I want to just finish by raising a few of the questions that I think are themes in this meeting. We sort of started in organizing this meeting with a grid of rows and columns, and the rows I think were infections, and the columns were topics. So surveillance and modeling and genetics and genomics and other topics. And we began to see some connections among these, and we thought it would be best to organize it more or less by organism, or at least group of organisms, so that's how the program is organized. But I want to emphasize some of the questions that I think will be recurring themes in these discussions. One of the ones that's been of particular interest to our research group recently is the question of why is multi-drug resistance so common compared to single drug resistance. And it's true in many different organisms, but this was the figure that brought it home to me. This is the proportion of isolates in the United States of gonorrhea from the CDC's GISP surveillance program, which are resistant to or sensitive to various drugs. And what you can see is that 3/4 of them in 2007 were sensitive to all 3 of the drugs that they test for, penicillin, tetracycline, and quinolones. And then the largest next slice is the one that are resistant to everything, to all 3 of them, and another one that's resistant to just tetracycline. But the point is that multi-drug resistance is overrepresented. And if you talk to, one reason we thought it would be fun to have different organism communities come together in this meeting is that if you talk to anybody who works on one bug, they know the answer to this, at least on many bugs. We think we know the answer. And the problem is that the answer we are pretty sure of is different for almost every group of organisms. And that might be true. It may be that it's just a different story each time, but it makes one wonder whether the obviously true story for one might actually have something to do with the others. So for nosocomial infections, we talk about linkage on plasmids of different resistance determinants and the fact that the hospital is kind of a high-use environment. For gonorrhea, there's at least some support for the notion of importation of multi-drug resistance from high-resistance countries, and so this is a sort of Walland effect in population genetic terms, where you see a mix of two populations, the pan-sensitive and the pan-resistant, and then you see a tendency of the resistance genes to assort with one another. In TB, we talk about how each resistance mutation facilitates the next one because of emergence during resistance. In the pneumococcus, this is also a striking phenomenon. I haven't heard a really compelling answer. There will be some discussion of that in Christoph Fraser's talk today, I think, or tomorrow. So anyway, I think when you have 4 or 5 different answers to the same question, you might wonder whether some of them are missing some larger point, or maybe it really is just every organism is different. Another, I think, related question is why, despite continuing selection by antibiotics, we continue to see sensitive strains in many populations that haven't gone away. 2 examples of this, both from strep pneumoniae. This is erythromycin resistance in pneumococcus in Europe in different countries, and it's not a lovely graph because it wasn't meant to show this point, but the groups of bars are the proportion resistant in each year, and what you can sort of see from looking at it is that number isn't changing enormously. It varies a lot between country. Each group is a different country, and you can see that on the left. The yellow countries are low resistance and the red countries are high resistance, but it's not going up appreciably in most countries. It just seems to be at some sort of equilibrium. And yet we know from another study in Israel of otitis media isolates that the proportion resistance can change dramatically over a season as antimicrobial use changes. So it's not that the bug doesn't know how to change quickly. From September to December, resistance can go up by many tens of percents, but somehow it doesn't change very quickly once it's established a level in a country, and we don't know why. This is a busy slide, but I think the question that I want to raise here is how do we use data, surveillance data on resistance, from what geographic or other level to make decisions about how treatment should work? And again, this is a case where there's a lot of diversity across organisms, possibly quite well justified, but I think it'll be an interesting discussion to see if we can make any common ground or whether there should be any common ground between these infections. So in flu, from the CDC guidance, the recommendation is to monitor local antiviral resistance surveillance data for prescribing decisions. In gonorrhea, there's been a history of updating the recommendations as soon as 5% of organisms of isolates are resistant in a geographic or sexual preference group to switch the recommendation to another newer antibiotic or a different antibiotic that doesn't have so much resistance. In TB, it's much more about patient-level susceptibility testing. And there's variation in many other organisms. And I think one of the themes of some of the talks will be trying to make the surveillance question precise so that we can actually get better answer to that question, perhaps at the expense of answering other questions. In mathematical models, which you'll hear a lot about, I think one thing that really puzzles me is what are the right characters to have in these dramas? So a model has different characters interacting: susceptible, colonized, uncolonized, resistant, colonized, patients, healthcare workers. These are 2 models published around the same time, which have different characters in the drama. We considered the drug-resistant organisms, but we didn't worry about the healthcare workers. They considered, for a different infection, the healthcare workers, but not the drug-resistant strains. And so I think a lot of these questions of who should be interacting with whom, how we include antibiotic use in the model, if at all, All of these are quite fundamental and not well answered. So I'm going to skip my last two questions in the interest of keeping to my own advice to the rest of you, which is to enjoy the meeting, to ask the speakers to keep to time, and we will have a long time for discussion at the end of each session. Please ask hard questions in that discussion, and lots of them. I hope it will be an active discussion. And really I hope we can think about what each of our favorite bugs can teach or learn from other people's favorite bugs. And I don't really literally mean that. I hope we can share our good ideas a little bit faster than they share theirs, and have as much fun.